Welcome to Known Unknowns. Two neutron stars slammed together far away from Earth. The energy of their collision lit up their corner of the sky with a brief flash of gamma radiation, followed by a softer, longer-lasting glow across the electromagnetic spectrum. Peering into that fading light, researchers spotted an unusual infrared signal, the first ever recorded signature, they believe, of a newborn cosmic behemoth, a magnetar. A magnetar is a neutron star with an unusually strong magnetic field. Astronomers have spotted magnetars elsewhere in the universe, but they've never before seen one being born. This time, researchers suspected they'd spotted a newborn magnetar because of an unusual pattern of flashing light. First, there was a short, ultra-bright burst of gamma radiation, GRB. Then there was a longer-lasting, glowing kilonova, a telltale sign of neutron stars colliding. And that glow was much brighter than usual, suggesting a phenomenon astronomers had never seen before. To detect neutron star collisions, scientists look for both short GRBs and longer-lasting light sources from the collision. Under normal circumstances, said Wenfei Fong, a Northwestern University astrophysicist who led the research, the glow left over from a neutron star collision has two parts. There's short-lived afterglow, which lasts for a couple days and results from material speeding away from the collision and slamming at high velocity into the dust and gas between stars. And then there's the kilonova glow of stirred-up particles swirling around the collision site. The recent event, called GRB 200522A, had a visible kilonova, but something was different. Scientists know from their models and previous observations how bright a kilonova should look. GRB 200522A was much brighter, particularly in the infrared part of the electromagnetic spectrum. This was 10 times brighter than any of previous observations. To explain why the kilonova was so bright, the researchers needed to figure out what new ingredient was present in the aftermath of the neutron star collision. We settled on a very large magnetar, Fong said. Like a whirling figure skater bringing their arms close to their body, the two orbiting neutron stars combined to form a faster spinning magnetar. Its powerful magnetic fields acted like the blades of a blender, stirring up the already energized kilonova particles, making them glow even brighter. There are other explanations, too, the researchers said. One possibility is a reverse shock. Two waves of the fast-moving particles from the afterglow might have slammed into each other. If conditions were just right, that crash might mimic a newborn magnetar. Similarly, some unexpected, decaying radioactive particles in the kilonova might have made GRB 200522A glow brighter. But Fong said both of these scenarios are unlikely. Assuming it is a magnetar, Fong said, future observations should reveal radio emissions from the distant site. And one day, the James Webb Space Telescope, not yet launched, should be able to peer further into short GRB sites, revealing still unseen details of these collisions.